And the formula I have on the board is what you use to determine the period of an oscillating spring. It's the formula that you would use in conjunction with some other things potentially to answer all of these questions. You may have to, for some of these questions, use the principle of the law of conservation of mechanical energy to find missing pieces of information. You may also have to use the fact that the period is equal to the reciprocal of the frequency, or the frequency is equal to the reciprocal of the period, depending on what the question is asking you. So between that formula on the left, the formula relating period and frequency, and conservation of mechanical energy, I think you should be able to answer these questions. However, life is not always that simple. Just because I say you should be able to doesn't mean you didn't have problems. Does anybody have any questions you would like me to go over here? Go ahead, Aoki. Number 5. So we have an object that's in oscillation on a spring, and you're given the value of the spring constant. It's along a frictionless surface, which again is laughable, but we're here to practice physics, and when it comes to applying physics and you get into engineering maybe, you would start off with analyzing frictionless surfaces, and then you would start analyzing reality. But this is a physics class, not an engineering class. The frequency is given to you. What is the mass? The formula that's going to be useful here is the one we learned, which relates the mass and the spring constant to the period, except that we're not given the period. Don't forget, everybody, and I should have reviewed this right at the beginning. We're coming back from a weekend, and I kind of forgot that for a second. The period is how many seconds it takes to go up and down once, or back and forth once, depending on which way the mass on the spring is oscillating. But the period is related to the frequency, because the frequency is how many oscillations per second it makes. So period, capital T, is time per oscillation. Frequency, F, is number of oscillations per second. They're reciprocals of each other. And since you know the frequency is 1.5 hertz, and by the way, on your last exam, there was a question that asked you, I think, for the period, and I didn't tell you it was capital T, and I didn't tell you it was measured in seconds. Everybody, I think, got 0.29, but some of you weren't sure whether it was 0.29 hertz or 0.29 seconds. A period is always a time. Okay. Can you confirm for me, Aoki, that when you take the reciprocal of that, you get 0.67? Actually 0.66666. And the reciprocal of hertz is seconds. And now what we can do is put that in here. But we're going to be doing some work today with a lab where we have to work with this formula algebraically without numbers in it. Let's do a bit of algebra here and square both sides. That way, and listen, this is not a math class, but I tell my math students this all the time. That idea of, quote, simplify in math literally means make it simpler for yourself. Square roots are complicated. How can we get rid of square roots? Well, we can simplify things by, in this case, squaring both sides of the equation. Getting t squared equals 2 squared, which is 4, pi squared, which is written as pi squared, m over k. Are you okay with that, everybody? I'm taking the opportunity to teach you some math, my math philosophy of making things simpler. Well, how can we simplify that current equation? The fact of the matter is, fractions are more complicated than not fractions. So, how do we get rid of fractions? Well, let's multiply both sides by the denominator. This is what we mean when we say we're simplifying it. We're turning it from a Math 20 question I know this is physics, but the math of it goes from being a Math 20 question with radicals to a, other than all the variables, to a grade 8 question with fractions, to an equation or a mathematical statement. Sorry, I'm talking and thinking at the same time. The k's cancel. So I now turn it into a mathematical statement, which, other than the variables and the fact that we have pi there, is really kind of an elementary school idea mathematically. We're multiplying some stuff together and it equals the product of some other things. Now we can put things in. Do we know, oh, we want to find the mass. I would go one step further here and just say, if we've come this far, why not travel a little bit further? We're so close to the answer algebraically. Let's just write the answer algebraically. That will be the mass of any object in oscillation if we knew the period. And now it's just a matter of putting in k, which was 115. And you know me by now. I think putting in the units would only serve to confuse visually what's going on. If it's written response, you want to do the units on paper and then maybe do scrap work on the side without units to help you get the answer. Multiplied by that period of 0.6 repeating squared divided by 4 pi. Remembering, of course, you better put the 4 pi in brackets or do like I do, divided by 4 divided by pi. But, and I have got an error here, don't I? What is it, Alex?
Pi isn't squared.
The pi isn't squared. I squared it up here when I squared both sides, but I neglected to write that all the way down. And again, this is literally not an excuse. I gave up a long time ago about worrying about, oh, I made a mistake in class today. You're going to make mistakes. What you want to do is be careful enough to minimize the mistakes. You're not going to get 100% on everything all the time, and neither will I. But we want to concentrate and work hard enough and careful enough that you minimize those errors. So 115 times the 0.6, I think that's sufficient for decimals. You could obviously put 2/3, which is what 0.6 repeating is. And now I want to divide by 4, and I want to divide by pi squared. And that's just how I operate. If you want to operate by going divided by bracket, 4 pi squared, you can. This should give us the answer, 1.29 kilograms, and it does. Good? Okay. Other questions? Go ahead, Gabrielle. 8. Okay, let's look at number 8. We have a mass of an object that's in simple harmonic motion. That's what that SHM means. On a spring, the maximum displacement is given, the period is given. What's the maximum acceleration? So when you have a mass oscillating on a spring, this goes back to what we did a few days ago. And I'm going to quickly construct 3 diagrams here. The first diagram is going to show the mass when it's compressed on the spring as much as possible. I shouldn't say the mass is compressed. It's going to show the system when the spring is compressed as much as possible. So we've got that, and we have a box, which I have to wait to show up. And that's compressed as much as possible. So this is a point in the oscillation when it's stopped moving towards the wall and is about to change direction. I'm going to draw one here, and I'm going to draw one here. And this right here at the bottom is the equilibrium position. And what that means, everybody, is that if that's the equilibrium position, it's going to continue moving to the right and stop some distance away on the right. And then it's going to go back to the left to the equilibrium position. It's going to continue to compress to this middle diagram, and then it's going to have full compression over here. And what I'm getting at is that this is where x equals 0. This is where x equals the amplitude, and this is where x is between 0 and the amplitude. Okay? If this is the equilibrium position, then right here, and I know it seems like I've gone way off the path here, okay, but bear with me. If this is the equilibrium position, then Fs, which is Kx, Fs here is 0, because x is 0. It's going to be moving really fast there, but the force on it is nothing, which means that if the force is 0, the acceleration is 0. Right? But the kinetic energy there is all the energy. No potential energy at that point. And what I'm doing really is reviewing what we did a few days ago, because we need to do that to answer this question. When I look at the top, and I don't really have that much room, but that's okay, I'll just do it this way. When I look at the top, since Fs equals Kx, and since x is as big as possible, this is going to be where the force on the mass is the maximum value. But since F equals ma, this is where the acceleration is maximum. So now let's cut to the chase here. What is the maximum acceleration? Well, that means we need to know the spring constant, and we need to know the maximum displacement. Do we know the maximum displacement? We do. Okay. So if we could figure out the spring constant, then we could multiply the spring constant by this 0.03 centimeters converted to meters to get the biggest force, and then divide by the mass, which we know. So how are we going to find the spring constant? Well, there's a couple of ways we could do it. One of the ways we could do it is to say that the potential energy here is equal to the kinetic energy at the bottom. But that's a dead end because we don't know how fast it's moving. Excuse me. Good morning. So that's a dead end. However, we do have this formula. And it turns out that my entire explanation here, which is the review of everything we learned a few days ago, was not really necessary. All that's really necessary to answer this question is you understanding that at the maximum displacement you will have the maximum force, and the maximum force means the maximum acceleration, so we need to determine the maximum displacement, or use it in our calculation. And we also need the spring constant. So what we can do now here, Gabrielle, is use this formula to find the spring constant, which I will do with you in a minute. Once we know the spring constant, we can calculate the maximum force using Hooke's law. Once we know the maximum force, we can divide by the mass using Newton's second law. You know me, sometimes I want to be very perfectly accurate in what I say. Why are we allowed to set this equal to ma? Aoki.
forces are canceled
I
out.
love the way you said that. You were going to say it's the only, and then you said, well, it's not the only force, but all the other forces cancel. In other words, that Fs at that point in time on the top diagram is the net force. Because when you add the force of gravity down and the normal force up, they cancel each other out because they're equal but opposite, so you're left with that. So let's get to work now on this. And then we'll get started on some lab work. What were we told here? The period is 0.5 seconds and the mass is 0.025 kilograms. Period is 0.5 seconds. The mass is 0.025 kilograms. Alex, did I get that right? This is 8.
0.025.
Okay. So I've got T equals 2 pi root m over k, which means T squared equals 4 pi squared m over k. You're okay with that? I'm going to cross multiply to get kt squared, or multiply both sides by k, however you want to justify this move. And that means k is equal to 4 pi squared m over t squared. And this, I think I've mentioned this numerous times. This is the beautiful thing about algebra. You do this here, you don't even need to write down any numbers, really. 4 times pi squared times the mass, which is given in the question, divided by the period squared. This is k. Now that I know what k is, I can say that the spring force equals the net force, and if I make this as large as possible, this is as large as possible. Were we after the acceleration? Okay. So the maximum acceleration will be the force on the spring over the mass on the spring. There's my k times the mass. Can you tell me, was the maximum displacement 0.03 centimeters? So that's 0.0003 meters. I have to divide the centimeters by 100, and then I divide by the mass. So about 4.7 times 10 to the negative 2 meters per second squared is what I got. All right, so we are doing a lab today. I was originally just going to give you the task and have you do it, but there's something about this that's a little bit more complicated, and I don't want to just leave you high and dry here without any help. Okay. So let me hand out the lab. This will be what you're going to turn in to me. I'm going to say this will be due Thursday. We're doing some other things between now and then. And if you're not here today, which means you are watching the video, I will be emailing you a copy of this which has hypothetical data, and as usual, you are still expected to complete all of the work. It doesn't hurt when you run into those. It just kind of surprises me. Did you? You got one. Okay, good. One of the types of analyses that we do in Physics 30 a lot, which Physics 30 students struggle with, is a graphical analysis. And you're going to be doing a graphical analysis here with your lab. So the first thing to note in general is what you are doing in this lab is you are finding the spring constant. Does yours say finding a spring constant from a spring? I meant to edit that. I mean, there's nothing technically wrong with it, but I meant to say from the period of a spring. You don't have to change the title. But the basic idea is you found the spring constant for some of these springs in your Hooke's Law lab in the last unit. This time you're going to be finding it by measuring the period. There's a relationship between the period of a spring and the spring constant. So when you look at this formula, there are three variables, right? There's T for period, M for mass, and K for the spring constant. Well, but the spring constant is not really a variable, it's a constant for the spring you're going to have. So if you set up your station here, this is spring D. This is spring D. No matter what mass you put on this and what period you end up determining, K is a constant here. So your two variables are the period and the mass. And you can see based on the table I've given you that you're going to be finding the period for 10 different masses. You're going to start off with 0.3 kilograms, which means using a 0.2 kilogram or 200 gram mass with a 100 gram mass hooked on it, and you're going to be determining the period. Now, with smaller masses, it's very easy for you to pull it down too much so that when it goes up, the string loosens. You don't want to do that. You want the string to keep its same length. So it may vary back and forth, like it may drift back and forth. But if you look at where the top of this ring on the spring is, where the string ends, the string length is not changing. And I think you know what's going to happen here because we kind of did this, I think, on Friday, didn't we? You're going to have to set this in motion, use a stopwatch, and I'm not going to I have stopwatches if you need one, but you have stopwatches on your phones. And with a partner, you're going to measure 10t. You're going to measure the time for 10 complete oscillations, so that would be starting now, 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. Start at the bottom, stop at the bottom. But you don't count the bottom as 1, right? So to get a larger mass on there so I don't have to talk so quickly in showing you this. By the way, when you put the 1 kilogram mass on or heavy masses on, don't put it here and let it go. Gradually bring it down till you can tell it's kind of where the equilibrium position for this mass will be. Then you can bring it down a little bit and get a nice oscillation going. So when you start, you go start, then 1, 2, 3. You don't count the first bottom as 1. That's where we start. And I think collecting the data is going to be very, very straightforward. I don't think there are any questions with that. What do you do then? Well, you're going to do 3 analyses, and you can see up here I've got under analyses, analysis 1 will be algebraic. Let's talk about that first. Basically, you're going to, I hope it's obvious, you're going to divide your times that you measure by 10, which I hope you don't need a calculator for, just move the decimal. Basically, what you're going to do in the first analysis is use the formula to calculate the spring constant. That's what I mean by algebraic. But I only want to see your work for the third data set. So when you copy your data here, whatever you have for the t, I want to see your work with this mass and this period in order for you to determine, not sure what happened there. In order for you to determine the spring constant. So up here at number 2, I think, no, number 1, calculate your spring constant. I want to see your work. All work means units, correct number of significant figures. I would say that since we have 2 decimal places for the mass, and you're going to probably have at least 2 for the times, I would say 1 decimal place for k. I have a feeling it's going to be in the teens or 20s for k for most of these springs. So if you get 25.286, record 25.3. Number 2 says calculate the spring constant for the other ones, so you're going to populate this table with the results of your experiment. I don't care to see your calculations for that. Number 3, what's the average spring constant? I do want to see how you calculate the average. I know you know how to do it, but I want you to write it down. And record the average here. Clearly, there's a spot in all of the tables for you to record the letter of the spring. Part of your mark is going to be how close you get to the results, how close your results are to what they should be. Now the graphical analysis. Analysis 2 will be graphical, where you actually use graph paper to complete the graph. Analysis 3 will be graphical, where you enter the data into your calculator and do a linear regression. But I'm going to teach you now the proper technique for a graphical analysis here. In this experiment, this is the responding variable, and this is the manipulated variable. And you'll want to pay careful attention to this, because somewhere in the lab I'm going to be asking you to explain what the connection is between the slope of the line and the spring constant, which is what we want to find, and use that relationship to determine the spring constant. Not only do you have to know how to use the slope to find the spring constant, you're going to be expected to explain why what you're doing works. Okay. So when we have a graph that we construct in science, we want the responding here and the manipulated here. But we also want a straight line. Now, those dots are in a pretty straight line. I don't think you're going to have much error in this experiment. If you're watching this video and I'm going to be emailing you some hypothetical data, I've introduced some error in some of that data. But do you remember when you did the Hooke's Law lab, your data was pretty much exactly linear, I think? I think if you do a good job here, there's no reason why your data should be all over the place. I think it should be pretty linear. Now, the only problem is if you plot T here and M here, you will not get a straight line. You won't. You get a curve because of that square root. And we don't need to worry about the nature of the curve. But what I can do is take this equation, 2 pi root m over k, and think of it this way. And then I can take it and think of it this way. And then I can compare that to y equals slope times x. And I'm not putting the letter m for slope because we already have an m in the equation for mass. What does this mean? I've been having difficulties with my highlighter today on my computer. Oh, it's back to normal. What it means is that if you plot period on the vertical axis and the square root of the mass on the horizontal axis, that 2 pi over the square root of k will be the slope of the line. We've done a few graphical analyses, but what I want to really continue to hammer away on here is that slope is not defined by y over x. It's not defined by y over x. Don't think of slope in physics as y over x, because it's not. It's delta y over delta x. But more importantly, the slope is not defined by y over x. The slope is defined by what you multiply x by to get y. And I know mathematically there's no real difference, but I want you to draw this kind of analogy all the time, where this is the slope because this is y and this is x. What this means is that in order for you to get a straight line, you have to plot the square root of m here. If you don't plot the square root of m there, you will not get a straight line. So now if you take a look at your handout, it says for analysis 2, it says complete the table below. Well, we've got another column now. You're going to have your periods that you already know from the first part of the analysis, but then you're going to have to take your masses and square root them. And I'm telling you, record your root masses to 3 decimal places. Whether you can use all 3 when you go to plot them on whatever scale you've created is a matter of debate. It doesn't matter, but 3 decimal places will be enough. You may not need the third one, but you might need the second. Okay, so you do that, you make the graph. On the graph, determine the slope of the line of best fit. I do want to remind you that when you draw your line of best fit, you lay down a ruler where you think it best represents the data. And if these are your data points, they should be circled, by the way. Maybe not that big, but they should be circled. When you find your slope, you pick 2 points on the line that are not data points, and they have to be or should be reasonably far apart. I mean, I've marked some labs sometimes where somebody picks 2 data points here and they have this little triangle. Don't do that. The bigger your triangle, the less error you're going to introduce in your reading of the data and calculation of the slope. Okay, then it says, once you've done that, use the slope to determine the spring constant. So, listen, your slope is equal to 2 pi over the square root of the spring constant. So let's imagine for a slope, you got 0.38 seconds per square root of kilograms. Why are you going to get those units for the slope? Because slope is found by taking y coordinates minus y coordinates, which will give you seconds, over x coordinates minus x coordinates, which will give you root kilograms. So how would you figure out what k is? You'd solve this equation. I can tell right away the units are confusing some of you. What might make it easier is to take what we learned from earlier on. Why don't we square both sides of this statement, which would turn it into slope squared equals 4 pi squared over k. Why don't we multiply both sides by k to make it even simpler and get k slope squared equals 4 pi squared, which means k will be equal to 4 pi squared over the square of the slope. That's what you have to do, whatever the slope is. So in my example, it would be k equals 4 pi squared over 0.38 squared. You know, since this is written work, I'm going to want to see units there. Just ignore the units when you do the calculation. What would I get? 4 pi squared divided by 0.38 squared. My spring constant would be 273 newtons per meter. You'll notice I said newtons per meter because I know that's what K is equal to, okay? Do you remember I've taught you that a newton is a kilogram meter per second squared? Okay. If you look at the units of what we'll get here, you're going to have seconds squared over kilograms on the bottom. You're going to get kilogram per second squared. Turns out that's equal to a newton per meter. Just trust me on that. So that's what you're going to do for analysis 2. For analysis 3, you're simply going to load the data into your calculator. You would put your, I'm not going to write this down, but you might want to jot it down. Put your root m's in list 1. Put your periods in list 2. Do a linear regression to find the slope and find K that way. I don't want you to do any kind of percent error or difference or anything here, but you should get a K value in analysis 3, very close to the K value in analysis 2, very close to the average K value in analysis 1. Did I already say I want this in on Thursday? Thursday, I think, is fair. We're moving on tomorrow, but so you're not going to get a lot of class time to work on this unless you find it yourself, but I think that's fair. What do we have? 2, 4, 6, 8, 10, 12, 14. We have 15 people. I do not want groups of 3. I can have one group of 3. If there's one group of 3, I can live with that. But I don't mind people doing it on their own. There's not much to it. How many springs do I have hanging? 9, 3, 6, 9, 2, 4, 6, 8, 10, 12, 14, 15 people. I mean, we can have quite a few groups that are groups of 1 if you like. Groups of singularity. Any questions? All right, let's get at it. I don't think you really need anything other than the springs and the masses are on the table there.